Looking at 3.7, this is the linearization section, and going into the example number 2. This one says find the linearization of y equals the square root of 1 plus x at x equals 0 and use it to approximate 1.02 without a calculator. Then use the calculator, we can determine the accuracy of our approximation. So hang on one second, I'm going to just open up and get that calculator rolling here. All right. Oops, wrong one. Um, what I'm looking at then is f of x is my function. It's the square root of 1 plus x. If I evaluate this at 0, I will get x of 1 plus 0, or the square root of 1 is 1. That gives me the ordered pair of 0, 1. What I'm heading for is trying to write the equation of the tangent line, and for that we needed the point, and we also need the slope at 0. So to get the derivative, let's take the derivative of our function. It's going to be 1 over 2 square root of 1 plus x. And then chain rule, of course, is just going to be a 1, so nothing more to add, and no need to multiply by anything. And then we get f prime of 0 to find the slope at 0, and we get 1 over 2 square root of 1 plus 0 would be times 1, so we're looking at a slope of 1/2. That allows us to write the tangent line equation, and that tangent line then would look like y minus 1 equals 1/2 x minus 0. And awesome work there. Now, what we're going to do is take and use that tangent line to estimate f of x. So I will say that f of x is approximately, or can be approximated by, the linearization of my tangent line equation. And that linearization simply means let's get this solved for y so that y equals, or like y is f of x, right? And I'm going to add 1 to the other side and then plus 1/2 of x. And there is the linearization for this particular problem. We know we were centered over 0, so we're going to be most accurate when we hover next to x being 0, which in this case actually means that we're hovered over the point of the square root of 1, or we'll be able to calculate things out near the square root of 1. And you'll see that here in a minute. If I wanted to make my estimate of the square root of 1.02, well, if I look back at this function and the way it was created, that really means I'm looking at 1 plus 0.02, where x is the 0.02. So on this linearization, my function is going to be evaluating 0.02 instead of writing 1.02. And that'll give us a linearization at the location of 0.02. And that would turn out to be 1 plus 1/2 of 0.02. Half of 0.02 is going to be, oops, that's a weird way. 0.01, there we go. Half of 0.02 would be 0.01. So there's our estimation. Now, that would be for f at x being 0.02. I think for clarity's sake, I'm going to write down that the square root of 1.02 is approximately 1.01. Okay? Now, the next thing it talks about is, let's talk about the accuracy of this. Well, we just captured this, and our approximation was 1.01. If I want to find out how much error there is, you'll see that right up here is an error formula, and the error, let's do absolute value so we get the plus and minus taken care of, is going to be calculated by looking at the true value minus the approximate value that we just calculated. So in my calculator, I'm just going to key in what is the square root of 1.02, and we get that it's 1.099. So I have 1.00995 is close enough, minus my estimated value of 1.01 gives us a difference of that, oops, not divided, that minus 1.01. And, ooh, very tiny number, huh? And this number would be 0. It's a negative point, but we're absolute valuing, so I'm going to get rid of the negative. 0.1234, and then it goes to 495. So that is the error. Now, sometimes it's nice to just talk about kind of like scientific notation powers of 10. How accurate is this? Is it accurate to the tenths position, hundredths, thousandths? And for this one, our actual value would be less than 0.0001, and I will say then my error is less than 10 to the negative fourth power. And we could do the same on these others, and I will just quickly inform you on what this linearization would be. We would do the same thing that we did when we calculated out the 1.01. I would put in 1 plus 1/2 of 0.002, since that would be the x value. So this would end up the f of 0.002 would be approximated at 1 plus 1/2 of 0.002. And that I came out with a value of 1.001. If I take the true value and subtract the estimated value, my error came out with this value to the negative seventh, which then I could say is going to be accurate to 10 to the minus 6. And the last one here is going to be a little bit less accurate than the previous two, because now I'm a little bit farther away from my centering point. So this is going to be approximated by f of 0.002, which is going to be approximately 1 plus 1/2 of 0.2, and that's going to give us 1.1. And this error would be less than 10 to the negative second. And here we had an error less than 10 to the negative fourth. So you can see if this was designed to be the square root of 1 is where our estimation is kind of centered over. The closer I am to 1, obviously the less error I pick up. The farther away I move from 1, like 1.2, the less accurate I become. And you can kind of see that on a picture as well. Here's that 0.01 that we created for our tangent line. Here was the equation, y equals the square root of 1 plus 0. And as I hover in close to my value of x being 0, I'm really similar. The blue line and the red line are hardly discernible. But as you move farther away, your error, of course, is going to become a little larger and a little larger and a little larger. Kind of what we anticipated. Example 3 we did in class on the first day, so I'm going to move past that one. Then we're going to talk about differentials. And differentials, we can talk about dy dx is equal to the derivative f prime of x, and dy would be what we call the differential of y, and dx is referred to as the differential of x. The differentials denote really just a change in their values in y or a change in x. The difference between a delta y and a differential y is that differential y is going to be just infinitely small. We're looking at immeasurable differences. Now, delta x and dx can be the same, and I want to refer to this diagram that we're looking at here to help explain what we're after here. So if I have my tangent line in red, and we have the actual curve f of x in blue, we know we can write an equation of the tangent line, and that would be the differential or the slope dy dx. Okay, and if I move over from x some change of x, I can put in and calculate f of x plus delta x. And for the blue line, I would come out here, and that would be a representation then of the change of y that happened. I put in some change of x, and I get out this change of y. If I look at my tangent line here, when I put in some change of x, I generate perhaps a different change of y. And that change of y is going to be referred to as the differential y. Notice the differential y and change of y here are different. This one is a lot smaller. Well, it's all in perspective, isn't it? Than this one. We have some error going on there, but the difference between those. So there is a difference between dy and dx. However, if we start decreasing so that delta x is immeasurably small, and I bring it back over here where I have x plus delta x, then you'll notice that dy and dx are not, or I'm sorry, change of y and delta y, that change of y, and differential y, that difference is now not so great. So what we can do is use the tangent line to help calculate out things that we project would happen on the blue line, the original curve. So one thing we're going to do here is we're putting things into a format called the differential form. And the differential form, if we take this knowledge of dy dx is equal to f prime of x, and we sort of separate and bring dx up and over, we get dy. We can calculate what the differential of y is. We can look for this value, this small immeasurable amount of dy. And that will be, this is what's known as differential form. So the three problems sitting down here say put them into differential form, and that's going to be actually a very easy process. Let's take the derivative of y. I look to the right and I see that I have the t variable. So this will be the differential of y with respect to t. This is my independent variable. How much I'm changing t influences the resulting change of y. So change of y here, or differential y, is the dependent variable. And that'll give us 6t squared plus 10t minus 3. Now to go into differential form, I'm simply going to say then dy is equal to 6t squared plus 10t minus 3 multiplied by the change of value of x, so differential x. Oh, why am I saying x? It's t. We'll bring up the dt. Next is b. And a little product rule on this. So we're going to have dy dx is equal to 3x squared sine of 3x added with the derivative of sine of 3x would be a 3 from the chain rule cosine 3x multiplied by x cubed. Let's squeeze that in front. So I'd have a 3x cubed cosine 3x. Derivative of sine gives me cosine. Derivative of the inside gave me the 3. To put it into differential form, I'd have dy equals 3x squared sine 3x plus 3x cubed cosine of 3x. All of this times the differential x. And finally, C, we got an e function. Okay, what's the rule for taking derivative of e to some function? It's e to the u times u prime. So ours is going to be dm. Oh, there's q, so dm dq is equal to e to the u, so e to the 5q squared plus 1. And then chain rule would generate a 10q times the e to the u. Multiply up by dq, and we're in differential form. Now, if you told me a value for q and the value for dq, how much I'm changing q by, I can tell you the resulting change in m is what differential form gains us. Example 5 is a good example of the usefulness of these differentials. And this one says a machined spherical bearing was measured with a caliper. The bearing's radius was found to be 2.3. So if we just kind of measured this, okay, the radius, well, that should have been, I got diameter showing there, didn't I? But if we measured the diameter and halved it, it was found to be 2.3. So this would have read, what, 4.6 really, wouldn't it? With a possible error no greater than 0.0001. And so that's the accuracy of our measurement. What is the maximum possible error in volume of the spherical bearing if we use this measurement for the radius? Okay, so what we got to come up with first is, what is our equation? And then we can take some derivatives. What is r? And then what would be dr? What would the equation be? Well, we're talking about a spherical bearing. It is a ball shape, so volume would be 4/3 pi r cubed. If I take the derivative of that, I'm going to have dv dr equals 3 comes down, cancels with my 3, I get 4 pi r squared. And put it in differential form, and I can talk about the change of volume is equal to 4 pi r squared times the change in radius, or the immeasurable difference of that radius. So if we reread, it says the bearing's radius was found to be 2.3. So I know my radius, and this measuring device we know has accuracy to 0.0001. That is our dr then. So dv is going to be equal to, the change in volume will be equal to 2.3 squared times 0.0001. And that's going to be quite small, which is a good thing, right? We want this ball bearing to be as accurate as possible. And I came out with that dv would be less than 0.00665 cubic inches. All right, we will be doing all the homework. We've got page 1 through 6. Use a graphing calculator. Go ahead and graph these out. We are not quite ready to be able to do some of these limits. That'll come after our next section when we do L'Hopital's. So use a graphing calculator, look at the graph and answer the limit questions. And then some Day 2 worksheet stuff here. A lot of AP questions, some free response questions that gives you a good insight as to what the AP does on these linearization problems. Thanks for joining in. Talk to you soon.